order reactions, and we'll see the integrated rate equation for first order reactions. You can copy this later. I'll share the notes also. Now let's talk about first order reactions. Right, let's figure out the integrated rate equation for these. Let's see. So you have reactant, which is becoming product. Again, your rate needs to be, I'm using the concentration of the reactant. So that will be what? Rate is equals to minus the change in concentration upon change in time. And you know, by order 1, I mean rate is equals to K R raised to the power 1. Right? You don't really have to show the 1, because I mean it's raised to the power 1, so the same ही value होगा. So I can say minus dr upon dt is equals to k r raised to the power 1. Right? You don't even have to show this one. Okay, now I'm going to rearrange this. I'm going to take the dt there, bring this here, like swap these positions, and I'll get what? And I'm going to take the negative sign to the other side. So I'm going to get change in concentration of the reactant upon the concentration of the reactant is equals to minus k dt. Now I'm going to integrate on both sides. Okay, I'm going to integrate on both sides. And when you do that, you get natural log. आपको क्या integrate करना है? ये side और ये side. So the integration of dr upon r is basically natural log, which is ln r is equals to minus kt plus I, which I again is the integration constant. And we will figure out the value for this guy. This guy right here is your natural log. It is not the base 10 log. This is the e to the power raise e to get the value of x, right? So this is basically your natural log. Now you have this, so you have now let's say at t is equals to 0, my r is equals to r naught. Okay, instantaneous rate at t 0 hota hai, so let me say that my reactant concentration at that time was r naught. And I'm going to put that, substitute that value here. So it will basically become ln, which is the natural log r naught, is equals to minus kt plus I. T you know is 0. So it will be ln r naught is equals to minus k times 0 plus I. And that will give you ln r naught is equals to the value of I. For your zero order reactions, if you remember, Li was equal to the initial concentration of the reactant for your zero order. Over here, I is equal to the natural log of the initial concentration of the reactant, right? For first order reactions. Now, okay, so far I hope you're following. Now, you know, so ln, let's go back to this equation, right? Before we, the equation that we got after integrating, right? Before we substituted r naught. So let's go back to this equation, this one right here. So you had natural log r is equals to minus kt plus I, right? You know I is what? I is ln r naught. So can I put that here? So it will be ln r is equals to minus kt plus ln r naught. That's the value of I, right? So I substituted the value of I here. Do you see this equation also resembles what? Y is equals to mx plus c. Anyway, we'll get to that later. But now let me bring all the r and the r naughts together. So I can bring this guy here. When I bring this guy here, it's gonna what? Subtract. And obviously with logs, you know, if it's subtracting, that means it's gonna divide, right? I mean, it's gonna be upon ln r naught is equals to minus kt. And now if I want to make k the subject, it will be k is equals to ln. Now I want to make k the subject, right? 1 second. I'm just going to take this equation and move on to the next page. Okay. So I have this, and now I want to make k the subject. So when I make k the subject, it will give you k is equals to natural log r naught upon r times 1 upon t, right? Now let me say I want to find out the rate at t1, or let me say we have to figure out the equation at t1. So at t1 I can say my r will be equals to r1, right? So what was your equation? The first equation that we did was this guy right here, right? So let's see. So let's find the equation at t1. So it will be ln r1 is equals to minus kt1 plus ln r naught, right? This was your equation, right? It was ln r minus kt plus I. We substituted the value of I for this, and that's what you have, right? So my r is r1, t is t1 because at time 1, right? And I get this value for this equation for t is equals to 1. Let me find the equation at t2, right? Let me say at t2 my r is equal to r2, and I'll do the same thing here. What will be my equation? It will be ln r2 is equals to minus kt2 plus ln r naught. Obviously all of this is not required for you to know, but it's the derivation which I need to do in order to get to the final equation, right? So this becomes my second equation. Okay, this is at t1, the other one is at t2. Now let's subtract these two equations. Let me subtract 1 from 2. So when I subtract 1 from 2, what do I get? I'm subtracting equation 1 from equation 2. Let's see. It will be ln r1 minus ln r2 is equals to minus kt1 minus kt2, and these guys are the same, ln r naught, so that will cancel out, right? You got this? You further simplify this, it becomes ln r1 upon, now since it's subtracting, right? So it's subtracting to वो divide हो जाएगा, ln r2 is equals to k t2 minus t1. Okay, and then you make k the subject. When you make k the subject, it becomes 1 upon t2 minus t1 ln r1 upon ln r2. So this is when you have to find out the rate between two given points, like between two different times. So you can use this equation to figure out the integrated rate equation to figure out the rate or the value of k, right? Now, I told you that this equation right here resembles y is equals to mx plus c. This one right here. I told you this resembles y is equals to mx plus c. Let's look at that. So you had natural log reactant minus kt plus ln r naught. This was the integration constant, right? So this equation is y is equals to mx plus c, where your y-intercept is equals to what? It is equals to, yeah, I'll just go back 1 second. So this equation resembles y is equals to mx plus c, right? Where your y-intercept basically would be what? The natural log of initial concentration, or R naught, okay? So you have y is equals to mx plus c. Right here, you will have your, I'll just go back in a bit. Just give me a second. Let me just finish this. So you have y is equals to mx plus c, right? This right here would be natural log of r. This right here would be your time, right? And your slope again would be negative k. And your y-intercept would be what? ln r naught, right? Now, this is a natural log, right? So if you want to convert this natural log into the base 10 log, which is, if you want to do that, and if you want to get rid of this ln, what you can do is you can multiply the natural log by 2.303 to convert it to the base 10 log, right? So the final equation that we figured out here was this, right? Now, if I want to get rid of this, I can multiply this equation by what? 2.303 to convert it to a base 10 log, okay? So if I want to do that, I'll just deal with T2 minus T1 as T, okay? So if you want to convert this into base 10 log, what you can do is ln2 log is multiplying by 2.303. You have to multiply the natural log by 2.303. Okay, so what will we do here? This will be k is equals to, you're multiplying by 2.303, so there will be 2.303 upon t, right? Where t is the change in time, t2 minus t1. And this will now become what? Log r naught upon r, right? Okay. So if you want to convert it, you can convert it by multiplying it by 2.303, or I'll just use this equation right here for you, where you had k is equals to 1 upon t natural log r naught upon r. If you want to remove this and make it a base 10 log, you can just say k is equals to 2.303 upon t log r naught upon r. Okay, and now once you have this, you can further simplify this, and this will be what? Log r naught upon r, okay, is equals to kt upon 2.303, where you see this k is a constant, right? So can I say that my time is directly proportional to the log of concentration, right? If you increase time, the value of log r naught upon r will also increase, right? So if you have this thing right here, if you have the value of log r naught upon r plotted on the y-axis, and if you have time on the x-axis, what type of a relationship do these two have? They have a direct relation, and that's why you will see a straight line. And what will be your slope? Your slope will be kt upon 2.303. But do you see, do you understand this? Do you understand that how k is a constant value? So t and log of the concentration is a direct relationship. If you increase time, this will also increase, right? And this is for your first order reactions. This is for your first order reaction. And what are first order reactions? Examples, I'll just do like two examples for you, and then I'm going to end this video. Okay, so first order reaction, the examples for first order reactions are decomposition reactions. Decomposition can be radioactive or any other compound decomposing. So like decomposition, for example, N2O5 can decompose into 2NO2 plus half O2. This is a first order reaction, right? Radioactive decomposition could be radium 22688 decomposing to give you helium, right? So this again is what? First order reaction. And all of these, if you have all gaseous reactants or products, then you will be using, instead of concentrations, you will be using what? Partial pressures. And I'll just get to that after I'm done with this right here. Okay, so these are examples of first order reactions. We are using concentration. If you have all gases, then you will be using partial pressures. Okay.